Today, our first question is going to be a tree question called same tree. So let me share my screen. Okay, so this would be the question. So, since there's only two people here, maybe we can ask you like of your opinion. So would you like me to do it in C++ or JavaScript? These are the two languages that I am familiar with for data structures and algorithms. JavaScript. Is JavaScript okay for you, Sharafuddin? Okay. Okay, I will try to do it in JavaScript. So, right, same tree. So basically, I'm given the root of two trees, okay, and they are structurally identical. Okay, so what does it mean by structurally identical? Meaning that the node structures are the same. Okay, so if there's one in the middle and one to the left, one to the right, there will be another one that is the same structure. But we don't know if the value of the nodes are the same. So we have to return true or false depending on whether the trees are completely the same, which is like the value is the same, right? Okay, so what we can do, okay, let me just pull out my Jamboard again. Okay, so okay, let's say I have these two trees, okay, and the value here is 1, 1, 2, 3, and 2, 3. Okay, so we know that these two are the same trees, right? Because these two nodes are the same, and then the right of it is 2, which the right of it is 2 also. Sorry, the left of it is 2, and the right of it is 3, which the right of it is 3 as well. Okay, so this is the one thing that we can see whether it's true. But how can we determine if it's false? Okay, so let's say what we can what we can do is we can compare at each node. Okay, so for example here, first we are at this node and this node. Okay, we will compare them two first. Okay, so if their values are not the same, then I'll return false because we don't have to check everything else, right? If these two starting nodes are different, then the solution would obviously be false. Okay, so the criteria for true is to check if the value of the two nodes are same. Okay, so inversely, if the value of the two nodes are not the same, then it's false. Okay, the value of the two node is not the same. Okay, so we can do this recursively by checking its children. Okay, so for example here, after I check that 1 equals to 1, I will recursively call the function to check for its left equals to the other left. Okay, so for example, what I can do is I will recursively check the left of the first tree and the left of the second tree. Okay, and then these two requirements would apply as well. Okay, so let's see the case where we are already at the leaf of the tree. Okay, so let's say if I'm already here at this leaf of the tree, okay, value 2, the leaves of the tree. So if the left of this value is a null, and the right of this value is a null. So if both of them are null, then it's the same, right? Okay. So it would be true if both are null as well. Okay. And if one of them is null and one of them is not null, then it's obviously false, right? So false if not both of them is null. Okay. So these are the 4 criteria. Okay. I can get this picture and I can go it through with you. So for example, Okay, if we look here in this tree, so now we are doing recursive. We are only checking one node at a time. Okay, so in our input, we only get the root node, which is this. Okay, so we check against our requirements. First, if both null, then we will return true, right? Okay, but since both of them are not null, so we don't return true. Okay, if one of them is null, only one of them. Sorry, my handwriting a bit ugly. Okay, if one of them is null, then I will return false, right? Because one of them is null and the other one is not null, meaning that it's not the same anymore. Okay, and if the value is not the same, then I will return false as well. Okay, because let's say if this is 1 and this is 2, then obviously the two trees are not the same, right? Then I can just straight away return false. Okay, so what happens when both of them are true? Then we can continue to check if its children are the same, right? So we can recursively call the left of the root and we compare it against the left of the root. Okay, so we can compare left and left here. So if I did not return anything, meaning that both is true, both value is the same. Okay, both value is the same. In this case, maybe I'll just write, I think it will be easier. Okay, if both value is the same, then I will recursively call function, okay, to check. Okay, so by doing this checking, right, I'm calling this recursive function 2 times. One is to check the left and one is to check the right. Okay, so this I'll just call this function 1 to check the left, okay, the 2 left nodes. And I'll call another recursive function to check the 2 right. Okay, so ultimately, if the tree is the same, then it will return true, right? So we need to see that 2 subtrees. Okay, so the left subtree of the first tree and the left subtree of the second tree should be the same, so it will return true. And the right subtree of the left tree and the right subtree of the right tree should be the same also. So these two should return true. Only I can say that the root, only I can say that the 2 trees are the same tree. So it has to be n, okay? So both has to be true. Okay, so I think I'm gonna just start coding and then you can see like how this works. Okay, so for recursion, we usually just check one node at a time and then we recursively call for the other nodes. All right, so what we can do here is, okay, following my logic first, I'm just gonna land out the criteria for absolute true and absolute false, okay? So this would be kind of like our base cases. So as I mentioned, our base case is that if P and Q are null, okay? If the 2 nodes are null, then I will return true. So if P and Q are not null, then I will return true, okay? And then if one of them is not null, then I will return false. So here I already checked if 2 of them are null, right? So if I do an OR operation here, okay, so if not P or not Q, okay, meaning if one of them is null, then I'll return false. Okay. And another thing, another reason that it could be false if the value is not the same. So here we already checked for nullness, so we don't have to worry about any errors that have been thrown because of the null node. Okay, so here I can just do if p.val, yeah, p.val doesn't equal to q.val, then I will return false. Okay. And then at the end, I can recursively call for its children. So recursively call children. I'm comparing the left of the left tree and the left of the right tree, right? So, okay, in this recursive call, I'm actually checking for the subtrees. So this recursive function actually breaks down a big tree into many subtrees, and we check the little subtrees first, and if the little subtrees are true, then we pass it back up, and if both of them are true, then it considered as true, and we pass it up until the root. Okay, so I can recursively call a same tree for the left node of P. Okay, so P dot left, and the left node of Q, so Q dot left. Okay. And I also have to check for the right node. And if both of them are true only, is the root node true? So do and then a same tree of P dot right and Q dot right. So this would be my overall solution for this same tree question. Okay, I think there shouldn't be any questions in the chat. Okay, cool. So this is the overall logic. I'm not sure about the JavaScript syntax. I hope this works. Let me just try to run the code. Okay. Let's see. So it's always returning true, true, false, false. Okay, so if, oh, okay, here. So here we need to check if both trees are null, right? So now I should put an exclamation mark to check if it's null. Okay, so let me just try to run this again. Okay. So anyone has any questions about the base cases and why we recursively call like this? So here I'm checking the left subtree and the right subtree, and eventually when I check until the leaf nodes, then this would be the base cases. Okay, so this is my, I would say this is like the more clearer way of explaining the logic, but actually you can just put them all together, right? I can just do this. If this or this or that, then I'll return false. And if not P and not Q, then I'll return true. Yeah. If you want it to be shorter, you can just like remove the braces, but that's not really the, okay, let's see. Oh, sorry. I have to check if one of them is not null first, because if it's null and I try to access the value, then it doesn't work like that. Then it will throw an error. So I have to check it at the back. As I was saying, you can make this into one line, but then it doesn't help a lot. There's not much point to it. Let me try to run the code. Okay, this works. Anyone has any questions? I think should not, right? This is a pretty straightforward question. All good? Both P and Q not null also return false. I think this was, okay, both P and Q not null. Are you talking about this first line? This first if statement? Not P meaning that if it's null. Yeah, that was incorrect. Yeah, okay, cool. Okay, so in that case, we can move on to another question that I had prepared. It's very, very similar. Let me change the JavaScript first. Okay, so here, the question is called Symmetric Tree. Okay, so the first question that we got is same tree, right? We have to check if we are given two root nodes, and we have to check if those two are the same trees. So now we are given one root node, and we have to check if this tree is a symmetric tree. So how do you define the symmetric tree? Is that if you cut in half and you fold it over, it would overlap completely. Okay, so this is not a symmetric tree. All right, but if this if this last element, right, this tree value is to the left of the two, then it would be symmetrical. Okay, so this is a symmetric tree. Anyone wanted to try this out? Or just like give some suggestions on the base case might be and how we can recurse through. Okay, so let me just copy this. Okay, so now we only have one tree. Okay, we can talk about the base cases first. So how do you define if the tree is symmetrical? Okay, remember what I said before about only checking one node, right? In recursive, we usually only do checking for one node and we recursively check for the subtrees. Okay, so if we assume that we only have one node, okay, is this symmetric? Is this symmetrical? Sorry, one node, it should have only one node. So like this, is this symmetrical? It should be symmetrical, right? Okay, so the criteria for checking symmetrical is that we have to check its left and right. And when we check to the leaf, how can we make the base case of it? Anyone has any idea? Okay, so for example here, right, what we can do is at each node, okay, so I'm at this first node, at each node, I can check if left and right is the same. Okay, I see someone's typing. Would you like to share with us any ideas that you have? Okay, yeah, I get your logic, right? So we are actually just checking its mirror. So we can make a function, okay? We can make a function. Let me make the function first, then maybe you can have an idea of how we can do this. So we can make a function whereas, okay, this function, it would take in two nodes, okay? So it would take in two nodes. And the idea is that these two nodes, we are passing in the nodes that should be mirrored to each other. So for example, when I'm at here, when I add this first node, okay, I will call the function that pass in its left and its right. Right? Then these 2 and 2 will be passed into the function. So how can we know if it's not symmetrical? Are there any base cases that we can check that we can straight away return false, or we can straight away return true if it's symmetrical? It is a bit similar as the one that we did just now with same tree. Try to like code this on your own. And if you want, you can send your code to the chat and I can take a look at it if you have time. Okay. If left child value equals to right child value, then we will return true. Okay. If these two values are the same, right, Sharafuddin? So for example, if these two are the same, okay, then you straight away return true. What if this value is not the same? Okay, so if this is 4 and 4, okay, if this is 4, yeah, and the rest is the same, okay, you are here and you check left, check right, they are both the same, so you straight away return true. And your solution is true, even though in this test case, it is actually false because down here, it is not the same, right? So in your case, right, in that condition, we should actually recurse through the subtrees, right? Because there is a chance that in the subtrees below, there could be false values. All right, do you understand my reasoning behind why we cannot straight away return true? Okay, so are there any base cases that we can straight away return true or false? Like what if we are already here? Okay, we are already at this 4 and this other 4. Okay, there are no more childs. So we know that if we look at these two, right, they are completely the same tree, right? So can we just return true if both of them are leaf nodes? Okay, so let me just, okay, so return true if both of them are null actually. Okay, because we are actually checking, we are actually sending down the values of the right and the left. Okay, so if both of them are null, then we will return true, right? Because there is nothing for us to check, recursively check anymore. Okay, if the two nodes are the same, there may be other nodes that are children that we need to check. But if it's null, then there's no more children, so we can just return true if both are null. Similarly, we can return false if one of them is null. Okay, of course, this has to go after the return true if both are null. Okay, and then same as the question we did before, we can also return true if, we can return false if the value is not the same, right? If the value is not the same, then there's no point of us continue to recurse the subtree because we already know that it's not symmetrical. Okay, so return false if value is not the same. How can we continue to recurse this? Okay, we know that at this point, okay, it's left, okay, it's left and right would be the first call, right? So what if I'm at here now and here? Okay, so I already have these two. How can I recursively call so that I can check if it's symmetrical? Okay, let me change color. Okay, so in my function, right, let's say if this is left and this is right. Okay, so I need to check if the subtrees are symmetrical. So meaning that the left of the left must be equal to the right of the right. Right? I hope it makes sense. Let me just change this to a highlighter. Okay, so the left of the, oh, this is not a highlighter. But it's okay. So the left of the left must be equal to the right of the right. Correct? And the right of the left must be equal to the left of the right. Does this make sense? Okay, so the left of the, the right of the left must be equal to the left of the right. And the right of the right must be equal to the left of the left. So we can recurse using this knowledge. Okay, so the way we can recurse is recurse by checking left of left must return true and right of right must return true also. Sorry, left of left and right of right. And right of right. Okay, so we will check left of left and right of right, and we would also check left of right and right of left. I hope this makes sense to you. So this would be our sort of like the logic behind our function. Okay, so the base cases is actually the same as same tree, right? It's very similar. Okay, but the way of recursing is different because now we are not checking if it's the same tree, we are checking if it's symmetrical. So we cannot just pass in the same left and left, right and right. It has to be mirrored, right? As mentioned by Sharafuddin. We can do it like a mirror. So in your mirror, if you put up your left hand, it's actually your right hand in the mirror. Does it make sense? So this is like the way we are doing it. Okay. Okay. So in this symmetrical tree, it's symmetric. Okay, since our function take in 2 nodes, right? But this base function, we are only take in this root node. So I can create a helper function. Okay, and this helper function would take in 2 nodes instead of 1. Okay, so left node and right node. Okay, oh, this is a arrow function. Okay, so according to our logic here, okay, if both are null, then I'll return true. If one of them is null, then I'll return false. And if the value is not the same, I'll return false as well. Okay, so if both is null, so if not left node and not right node, if not left node and not right node, then I will return true. Okay, and then else if, actually this could be an else if, doesn't matter. Okay, so else if not left node or not right node, so if one of them is null, then I'll return false. Okay, and also there's another scenario that I'll return false, is that if the value of the nodes are not the same. So if left node dot value doesn't equal to right node dot value, okay, okay, so in this case, I will return false. Okay. And then down here, I will recursively check for subtrees. Okay, so here I can just return. Okay, so I'm gonna remind you a bit here. Oops, where is my jump? Okay, so we are recursing. We are recursing by checking the left of the left and the right of the right. They should be the same, right? So we are putting these 2 nodes in one function call. Okay, so I can return I can return the helper of the left of the left. Okay, and the right of the right. So this should return true if it's a symmetrical tree. And we are also checking the right of the left and the left of the right. And this should also return true if it's a symmetrical tree. So these 2 must be true at the same time. That's why I put an and sign here. And this would be our solution. Let me try to run the cases. Undefined. Oh, okay, because I did not do anything with the main function. Okay, so this is our helper function, and it takes in 2 nodes. So how can we get started? We can just pass in the left and the right of our tree node, our root node. Okay, so I will return helper of root to the left and root to the right. Okay, so there is, let me check the constraints. Okay, so there is actually one edge case here. Can anybody tell me about it? Oh, okay, the time is already up, so I'll just let you know the edge case. Is actually fairly simple. Is that we have to check if the root node is null. Because if the root node is null, then there's no left of the root node, and it would give an error. Okay, so if the root node is null, meaning that there's nothing in the tree, then it's automatically symmetrical. Okay, so if not root, then I will return true. Okay, let me try to run this. All right, submit the code. Okay, oh, I did this 1 month ago. Okay, so these are the 2 questions that I covered today. A bit much because these 2 are easy questions and they are very similar. So I tried to put them together so you can see the pattern and the techniques that we can use while recursing through a binary tree. in order to find like if it's same, if it's symmetrical, or if there's any correlation between the trees. All right, I hope that you learned something for this session, and I'm gonna hand over to Marcus for the next question. All right, thank you.
Okay, so let me share my screen. Okay, well, the question today was looking at, uh, I'm very into arrays lah, and like I recently just had like an interview with an NFT startup. So they actually asked a lot of like arrays questions. So I think it's quite interesting that we can cover arrays. So rotate arrays is one of the, I would say one of the most, like one of the many popular questions that would be asked in an interview, like when they ask you about some arrays question. So this is actually like a very practical question. You could actually uh like face these questions when you go for interview. So it's a very interesting question to cover. It's actually not very hard. There's still different ways to solve this. There's two main ways to solve this problem. If you use the easy way, it's actually very easy. If you use the second way, it's not that hard. It's still quite simple, but it takes a bit of like thinking. So basically, what this question is that you are given an array. So let's say 1, 2, 3, 4, 5, 6, 7, and you're given a pivot. Okay, so so k equals to 3. So k basically is a pivot, like it's like a point. Let's say I can just point something at this part. So let's say k equals to 3. So this tree actually means an index. It doesn't mean the value tree. So in this case, it would be 0, 1, 2, 3. So actually, k should be here. Annotate this. Okay, so in this case, number 4 is okay. So this is your pivot. So what does it mean? It says that given an array, rotate the array to the right by k steps, where k is no negative. So rotate the array to the right. Okay, so to the right is something very important. So to the right, it says to the right. So when we rotate an array, how would it look like is where okay, so let me just show you what a rotation looks like. So let's say this is um, at step 0. I'll just say it's step 0. The array will still look the same as how it looks previously. But then if we move on to step 1, okay, that means we move 1 to the right. It it will become like this. It will become um, 7, 1, 2, 3, 4, 5, 6, and then step 2, it will become you just probably 6, 7, 1, 2, 3, 4, 5. Okay, at step 3, your array will become 5, 6, 7, 1, 2, 3, 4. So basically, if you see, this is how we say we rotated it 3 times. So 1, 2, and 3. So you get an array from this or from this form into this form, become 5, 6, 7, 1, 2, 3, 4. So it's actually not hard to understand the question. But the thing that is hard is how we can do this. Because because if this is like a queue, or like if this is like the data structure for this, if it's like a, how to say, if it's like a linked list, or it's like a doubly linked list lah, then we could do this like very easily, because we can just take something at the back, just move it to the front, then we get the result, and then we just do that for 3 times, and it's actually pretty simple if we do, like if we have like a linked list to manipulate this behavior. Or yeah, but the problem is we're giving it like a vector. So vector is like an array. Of course, you can do pushback, and I think you can also do insert at front. But I don't think we're not going to do this thing. We're going to like just treat it as a normal array and do the whole question as a normal array, because there's actually some ways that we can do it, which is even more efficient than doing a pushback. Like than doing like a taking an element from the back, put it at the front, taking an element from the back and put it at the front. Of course, like if you want to do it this way, it's possible. It's also at least in C++, if you have vector, you can do it with vectors. But I'm not sure if, like, let's say if I go to C, I think there's no vectors. If I use C, it's an array. So if I want to do like a pushback and then insert at front, it would be very difficult because it's the data structure doesn't support it. But I guess if you want to do that in Python or you want to do like in JavaScript, I think it's fine because like those kind of language provide this kind of like you can do it like this way, like just take something off the last element, put it in front, and then you can repeat for k times, you get the result. So but I won't do that. Okay, well, we're just going to treat this as like a normal array where we are not allowed to like do this kind of operations. So what we're going to do is, if you look closely, let's just ignore the first and second step. So we just compare like the input and the output. So the thing that we give and the thing that and the result of it. So 1, 2, 3, 4, 5, 6, 7. So this is our original input, and then this is our output, right? So for this, from this original input, we want to get to this output. So what we can see here is that if we still take like k, and we treat it as a pivot, right? So you can see that the pivot is at k, and you'll notice that everything that is before the pivot is changed. Okay, so everything before in the pivot, let's say this 1, 2, 3, it will be changed to the last three elements. So let's say my pivot is a 4. Before k, there's three elements. Then these three elements will become the last three elements of the array. So this is the first thing that we know. So let's just write this down. Characteristics 1 lah. So everything before k will become the last uh, last few elements lah. I will just say last few elements, and then use okay char one. Okay, char means for characteristic lah. So the second characteristics, you'll see that because of what because of like the thing that let's say if you change like 1, 2, 3 become 5, 6, 7, and then you see that like the original array like or 1, 2, 3, 4, it will be pushed back, like it will be pushed um further, like it will be pushed behind 5, 6, 7. So basically what you can do is you can take these three elements to the front, and you'll see that it actually gives us the result, right? Like it's actually what we want. So these are the characteristics that we can see from here. So if we know before k there's three elements, we just go to the end of the array, take three elements, put it to the front, and then we achieve our result already. But the thing is, it's very hard for us to like, if it's very hard to okay, let me just write the okay, everything is pushed back k times. So like what push back k times. So what do I mean like push back k times? You see number one in the end from this position 0, you'll move to the position 3. So you can just say like number one is push back 3 times. Like push back 1 time, 2 times, and then 3 times, which 3 is k, so you can just say k times. And this is true for every element. So like the 2 in the result, it will also be pushed back k times. So these are the characteristics that we can find. So from these characteristics, we can actually do something very basic and very simple. So I'll just go with the first approach, which is not so memory efficient, but then it would work. The first thing that we can do is that we can copy and we can get a copy of nums. So one special thing here is that you notice that this function actually returns nothing. It's a void function. The reason being that our challenge is to mutate this array in place without creating a new copy. But we can do it easier lah if we are allowed to like create a copy. So I'll just do it with a copy, which the memory wouldn't be so efficient, but we can just move on from there, then improve our solution. So I'll just create a copy of I'll just say this is a clone of the how to say of the original array that's given. So in C++, you can write this, or even better, if you just write this, your clone will be an exact copy of like nums. So there's a reason why we need a clone. So I'll just say copy the original array. Then the second thing is that um, we have a k, right? We have a k. So the thing is, this k, if we look at the constraint, it's the k, it can be very huge. It can be 0 to 10 to the power of 5, which is very huge. And if we try to, like, let's say in this second characteristic, if we try to push back an element's k times lah, and then k is actually larger than the array size, then we'll have problem because you're trying to push the element until it's out of scope, until it's like out of the bounds. If you do Java, they call it like bounds, the array bounds. So we have to make sure that this k, it has to be smaller than the, this is required, this condition is required. We have to make sure that this k must be smaller. Oh, I think I wrote it a bit wrong. Yeah, yeah, yeah. So the k must be smaller than the num size, which is the array size. It must be smaller. But but the problem here is like we could have get better, like higher k or like bigger k, and we have to handle that situation. So there's one thing that we can do. We can just do k nums dot size. So what does this actually do is that mod k to remove unnecessary steps. Unnecessary steps. So I'll just call it this way. Is because like, let's say if we have k is like, let's say 9, right? Say we have 9, and then I'll do like 9 modulus. Let's say we're using this same array, 7, right? Then what does 9 mod 7 give us? So we can actually check here. Let's check here. 9 mod 7. So 9 mod 7 is 2, right? So you get 2. So because, and then if you think about it, if you rotate an array lah more than more than its current time, you're actually just repeating stuff. So like if in this case 1 2 3 4 5 6 7, if I put k is equals 7, and then essentially the pivot will become at this place, right? Become at 7. And then uh if I try to, like, let's say I want to try to rotate this whole thing, if I rotate it 7 times, I'll still get back the same thing. Like if I take, like, okay, if I just try to do it like this step lah, I try to take 7, move to the front, 6, move to the front, 5, move to the front, 4, move to the front, 3, move to the front, 2, move to the front, 1, move to the front, then I'll end back with the same array. So if, let's say, if I have 9, instead of putting this k, like, instead of putting this pivot out of bounds, because like definitely you can't have like a k like bigger than the array size because it will go out of bounds. Instead of doing that, you can just put k at the pivot of 2, because you know that it is equivalent. Like it will be equivalent, like no matter how many times. If it won't, like, the number of rotation that you are going to do is not going to be bigger than the array size. So that is what we're trying to do here. Like mod k is trying to like reduce everything uh like to smaller than the array size, because no matter what, like if you do mod 7, the mod will not be bigger than 7. It can only be like from 0 to 7, but it cannot be bigger than 7. So yeah, so basically that's the reason we're doing mod. And so to reduce the number of like rotation that we do lah. Then from here onwards, what we want to do is that we know for sure there's two characteristics. One thing is that everything before k will become the last few elements, right? So because everything before k, so let's say k is like let me just put it back, k equals 3. uh, yeah, so everything, oh sorry, equals 3 should be here. Okay, so everything before k will become the last few elements. So what I can do is I can say I want to mutate everything before k. So I can just essentially just do like a for loop. Just go through like I smaller than k, I plus plus, because I just want to do some stuff. I want to do it up until before k. So up until before k, I can just do this mutation. I will set this to something else, to something from the clone. So let's just say we just mutate it to the clone. So I know like it's the last, like up before k is everything before ma. So like 0, 1, 2, 3, and then the clone I want the last 3. So in this case I want the last 3. So I can just do nums dot size minus minus I. I think sorry, minus k plus I. So minus k plus I. So in this case, minus num dot sign minus k will give me, okay, let's say the slash is 7. 7 minus k, k is 3, so it become 4. 0, 1, 2, 3, 4. It will give me 5. And in this case, I start from 0. So yeah, 5 will, I'll get the element 5. So the first element, 0, will become 5. And then 5 still remains. Okay, this is the original array. So at the second iteration, because I becomes 1 now, so it will come to this element. So 2 will become 6. And then because I only do up until k, up before k, so this tree I'll terminate at this place, and because I is equals to 2 now, so plus 2, then it will become 7. So you can see that there's a problem here, okay, because we only mutate everything before k. So now it's our turn. We want to mutate everything from k and from k onwards, means including k lah. So I'll just do int I equals to k, okay, and then I smaller than nums dot size. I'll do I plus plus. So now I want to do, so I want to mutate everything. So essentially I want to mutate from 4, 5, 6, 7. So the code will always be the same because the code we didn't mutate it. So the code will still be, in this case will still be 1, 2, 3, 4, 5, 6, 7. Okay, so let's say I want to change from 4, 5, 6, 7. What should I change? It should be 1, 2, 3, 4, right? It should be 1, 2, 3, 4. So I can just say it should be k minus I. Right? Wait, let me think about it. I think it's k minus I. K. So in this case, k is 3. Okay, k is 3, and then I is k. Yeah, so k minus I, which is 0. Yeah, I think it's 0. So this will become 1. And then at the next iteration, because I plus plus, so now I will become what is it called? I will become 4. Also 3 minus 4. Okay, not negative 1. Sorry. Not k minus I, but it's I minus k. So in this case, 4 minus 3 will become 1. So I'll take from this first index, and then become 3, and then become 4, and then in the end you achieve this. You get like the rotated array. So it's actually quite quick. It's actually for this solution, like it's O of n time, and it's O of n memory. Like the reason we have like the O of n memory is because we copy the original array. We copy the original array so that we can have a reference to see what we want to put in. So but there's a way to do this without using extra memory. Like there's a way to do this in O1 memory, which will save some memory lah. It will still be O(n) time, but we save some memories. So let's just try this. I think this should be just submit lah. This should be okay. Yep, so you can see that it works. But here's the thing. So you can see it actually uses a lot of memory, like 25.7 megabyte. If you compare with the C++ version, 25.7 megabytes memory use. So let's just do one more version that actually use lesser memory. Let's just so we just scrap all this. So essentially we can't copy a new array, right? So we can't copy a new array. So we have to do it in O1 time. That means we can use variable to store things, but we can only use like one variable. It's not like a whole array or something. So I can just call this temp. So used to store temporary values lah. Yeah, used to store temporary values. Then we'll have to okay, let's just go through an example of how we can do this, right? So 1, 2, 3, 4, 5, 6, 7, and then k equals 3. So the pivot would be here. So this is k. Oh, sorry. The pivot would be here. So what we can do is, like, instead of having like an extra memory, like a reference memory, right? We can also, okay, let me just, so we can also do one thing where we can just swap, like, okay, one, you can see like 1 and 7, right? You can actually swap 7 to the, sorry, you can, we can actually like 1, 2, 3, like this 3 thing, we can swap it with 5, 6, 7, right? And then we just have to do the swap cleverly lah, like to make sure everything is correct. So let's say in this case, I can swap 1 and 5, so this become 1. I can swap um 2 and 6, so this become 2. and I can swap 3 and 7, 3 and 7 become 3. Okay, so here's the problem. Like, how about the 4? Okay, the 4 has some issues where, like, it's not going to work because, like, it's not a valid array. But here's the thing. What if we do an extra step? What if we do an extra step to make it easier? So if we do it with an array like this, you see that we'll always end up with the pivot that is like hanging in the middle, which is not correct. But what if we can just like reverse the whole array first? Let's say every time I reverse the array first, so I make it become six. So I make it like this. Um, you see that my pivot doesn't actually change. Okay, my pivot doesn't actually change. Okay, but what I can do here is I can swap everything. I can swap everything. How to say up to k, and then I can reverse everything up to k. So if I can just reverse it. So let's say the end result is 5, 6, 7, 1, 2, 3, 4, right? So this should be the end result. Actually, we are very close to the end result. What we want to do is we did a big reverse on the whole array. Then we just reverse up to k, and just reverse from k onwards. So in this case, if I reverse up to k, it'll become 5, 6, 7, 4, 3, 2, 1. Okay, this is reverse up to k, and then of course the pivot doesn't change lah. K is still here. And then the next step, I just reverse from K onwards, which in this case, I'll just reverse 4, 3, 2, 1 become 1, 2, 3, 4. And then you see that we actually end up with the same result, but we didn't use any extra memory. Of course, we probably need a temp variable to store temporary value lah. But there's another way that we can refactor this to like even like it will be done in like 4 lines. Yeah, I think in 4 lines of code we can solve this thing. But yeah, let's just do it with a temporary value. We actually probably we don't need a temporary value because like in C++ there's a swap function. But we'll just do it like this first. So the first thing we want to do is reverse the whole array. So how to reverse an array is that we can do something like this. I smaller than num.size divided by 2 I plus plus. So okay, then we need to store the temporary value first. Temp equals to nums at I. Then we just swap nums at I to be, so what we want to swap it to. So let's say in this case, so nums at I is 0. We want to rotate the whole thing and become like this. So essentially it would be something at the back. It would be nums of nums.size minus plus I. I think it's plus I minus 1 plus I, because this is index of 6. So although the size is 7, we want an index of 6, so minus 1 and then plus 0, which is 6. And then we just have to turn that thing at the back, minus 1 plus I, just change it back to temp. So this is the reason of like using a temporary variable. So after doing this, we essentially just reverse the whole array, because like 1 change to 7, then 2, basically reverse the whole array, like in that sense. Then we have to reverse up to k. So let's just do this. So do it up to k, so k divided by 2, I plus plus. And we have to assign the temps also. Nums at I would be equals to nums at think about this. Okay, so we want to reverse up to k, right? So 7, 6, 5 to 4. So we would want to change it. Say 7 change with 5. Yeah, 7 change with 5. So 7 and 5. So nums I start from 7. Then this one should start from k minus I, if I'm not wrong. K minus I. Is it? Yeah, k minus I. So it should be equals to 10. Okay. Then lastly, we want to like do the last case where we reverse from k onwards. So this would be a bit tricky, but it's not that difficult as well. So we can still do this. Uh, in this case, we want the num.size minus k divided by 2 and plus plus. So we still want to store the temporary variable. Okay. Then we want to mutate it. So in this case, we instead of like we want to mutate k plus I because why? Because we want to mutate from k. We want to mutate for like reverse lah, not mutate 4, 5, 6, 7. Because I is from 0 ma. We don't want to change 1, 2, 3, but we want to change like from 4 onwards. That's why we have like a k plus I. It should be something um from the back. So like 4. It's so 4. It actually should change with like 1. So in this case, 1 would be nums.size minus 1 plus I. So yeah, so it becomes 6, 5, 4. Wait. So this is 6 plus I. Oh no, so it's not plus I, but it's actually minus I. If I'm not wrong. Think about it. Is it? Yeah, I think it is. So we just change this dot num.size minus 1 minus I should actually be equals to num set k plus I. So k plus I is where, no, sorry, should be 10 because like the thing would go out of sync. So basically this is the whole solution. We just reverse the whole array, reverse up to k, and reverse from k onwards. Let's just test this. I'm not sure if this work. I haven't tested it on with the test case here. Okay, we have some problem. Heap buffer overflow. Okay, we somehow access some memories that we shouldn't access. Let's see. It's number size minus k divided by 2 minus k squared. Uh, so size is 7 minus k 3, so become 4. Yeah. So divided by 2. Let me check back my solution here. I think I probably done something wrong. Minus 1 minus I per 10 minus 1 minus I. Yeah, okay, yeah, here. We should actually store k plus I instead of like just I. Something wrong again. Let's see. Where is it? So, oh, yeah, okay. So, yeah, so here we have to also do minus 1. The reason being that because, like, if we don't do minus 1, because it's smaller, then it's not like smaller equal, that's why we have to do like k minus 1. Else, like, the thing would go out of bounds. Yeah, and I think that's all. I think that's all. Wait, am I right? Okay, no. So this is actually also minus instead of plus because yeah, I think that makes sense because we want to like reverse the whole array, so it has to yeah. But like I actually don't like this approach. Like we have to do like temporary memory. I can still show one more thing. It actually it's much more simpler. But I can just show you this actually works and use lesser memory. For the last one, we're just going to like okay wait something wrong. Oh yeah, we forgot to do that thing. We forgot to like make the key smaller. Make key smaller than size because we can't access array like out of that thing, so we have to still do this key mod nums dot size. Okay, and this should work. And you should actually see the memory usage is much more lower. It's lower, but it's not lower by a lot. Not sure why, but it should be lower by a lot. And the last one is actually very simple where let's just delete all the comments to make this uh, even clearer. I mean like to be very concise lah. Because the thing is if we are trying to do swap in C++, you have a swap method that you can just use it this way. And then you can just like really let's say if you really want to make things concise, then we can do it this way. Probably some people don't like it because like it's too But it's too short and it's very hard to read. But I actually prefer it this way. Um, so we can also like just do this. So I can just say swap and then here and then here and delete this, delete this. Yep. And then let me just make this smaller so you can see that it's actually 4 line. Like doesn't like if you don't like it, it's not really readable. You can just put it here. Like the can just put it you can just put it like this. The only difference like with this and the previous solution, it's actually the same thing. It's just that we eliminate the temporary value, so the compiler can actually just directly do the swap instead of like saving something to a temporary value. But it's the same thing. It should give you the same result. They have the same logic. Okay, so error expected. But does it not compile with like swap or stuff? Okay, error expected. Did I just accidentally delete something? Numset key, blah 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 blah. Check. Did I just accidentally delete something? Uh, okay, never mind. Um, wait. Yeah, I'm not sure why this doesn't compile though. Probably because of like, oh, I think I did accidentally deleted this. Yeah. Yeah, then it should work. Yeah. Some like probably you don't see like very much different because like maybe they don't test big enough test cases. But that's the gist of it lah. That's the idea. So this should actually so this is the better solution where it still go OFN time, but you don't use extra memory. Yeah, you just use O of one memory, and that's basically the solution for this problem. Yeah. Is there any question to this? I have to clarify. Or is that alright? Do like a mirror? Oh, okay. So I think if that's alright, then I think we can end the session here, and then we'll have our code uploaded later on to the GitHub repo. And thanks everyone for joining.